Hi, this is Jim Plank with the last of the videos for the paper about converting between encodings in spiking neural networks. As always, if you are watching this video and you haven't gone through the main README, go to the main homepage for the repo for this paper and either read the README or go through the video for the README, and that'll give you all of the tools, an introduction that you need to understand this video. Now, we're working on a control application now, and we're doing a very similar thing as the last experiment. We're going to train with a spike inefficient encoder, and then we are going to make it efficient using conversion networks, and there will be some subtleties involved. The application is the well-known cart pole application. We have it as part of our closed source framework, although it works identically to the OpenAI GIMS pole balance. So you can actually use networks between one and the other. Now, what I'm going to do is I'm just going to show you. So we've trained a network that solves the hardest setting of the cart pole problem. In this setting, you are only given two observations. Well, here, let's just run the visualizer so you can see what's going on. This is, in fact, the exact network. Let's get rid of those little labels. Okay, here's the cart. So we've got a cart on a track. It has a pole that's balanced on top. Your agent, your AI agent, in this setting of the problem is only given two observations. It's given the x position of the cart and the theta angle of the pole. In the easier setting is it's also given velocity, which you see here in this visualization. But in this version of the problem, we are only given the position of the cart and the angle of the pole. And then your agent will run and determine, should I push the cart left or right? And then the goal is to keep the pole balanced, to keep the cart between the two walls. The normal parameters of this problem are incredibly simple. This is a much harder setting of the problem, which is kind of why we like to concentrate on it. All right, we'll get rid of that. If you want more info about the cart pole problem, here, just you can go to our homepage, go to publications, boom, cart pole is in open access, nice journal paper all about the cart pole, including input encodings that we've worked on and all the parameter settings, etc. However, this is not an advertisement for that paper. This instead is working on this paper. So now we're going to go to the repo here. And what we have is the following. As in the previous example, we have trained a neural network to solve this problem. Now, the way this neural network works is a little on the quirky side. Now, it is, let's go ahead and go to back so we can see the pictures. Okay. Here's the neural network. It is very small. The cart pole problems you can solve with fairly small neural networks. Now, there are 8 input neurons and 2 output neurons. There are only 2 inputs, okay, only 2 features, the x position and the theta angle. However, these are converted into spikes using a quote Argyle encoder, which I'm not going to go into the mechanics of it, but what it means is that each of these input values has 4 input neurons, and it's going to spike into 2 of them at each time, and the total number of spikes is going to be 9 into 2 of these 4 neurons, and those spikes will be spaced 3 time steps apart. Okay, so total of 8 spikes on any one neuron over 24 time steps. We run it for those 24 time steps, and then we count the spikes on the left and the right neurons, and whichever one spikes more, that's our action, with ties being broken towards L. Okay. Standard way of doing it. The reason I use this encoder is that paper I just showed you. When we did all of our experimentations, that ended up being the most effective encoder for this parameter setting of the problem. Okay, and that video that you saw was in fact this network working on that. Now, there's a little bit more quirkiness to it. Now, as before, so here, if we look in networks, we have two. We have an original and a converted. This is the original network, um, which we could look at, but it looks just like that. And if we look at the inputs, so now the inputs to this that are in the processor tool inputs um, are as follows. As with the classification experiment, we ran this using our closed source framework because we have application support with it. With that, we made sure that we printed out at each time step of the application, and there are 15,000 of these because it runs at a 50th of a second for 5 simulated minutes. It will print out what the observations are and then how that is turned into input spike counts. So what we have here is there are the 4 neurons for X, there are the 4 neurons for theta, and as promised, there are 9 spikes into each of those. Okay, and then you'll notice, right, our action is we push the cart to the right. Here's our output spike. We ran it, so we applied the input spikes, ran it for 24 time steps. Here's our output spike count, right? 0 on L, 7 on R, so that the action is push the cart to the right. And what you'll notice with that is that the X position changes not by much. The theta angle gets increased enough that actually changes what inputs get done. So before there were 7 to T2 and 2 to T3, now there are 6 to T2 and 3 to T3, and that's because it's moved, the angle has gotten bigger. You can kind of see as it runs, the angle gets smaller, right there it's getting smaller and smaller still, and that means that we end up shifting more towards T2, and in fact I bet here now we've already shifted all the way from T3, and now we're actually using T1. That's how the Argyle encoder works. Okay, so that's how the input processing goes. There's a little bit more to it. Okay, when we run this with our in the processor tool, we can look at the output count, and that output count should match that one exactly. There's the action that our application came with, and this one ends up keeping the poll up for all 1,500 or 15,000 time steps. Yep, so it's there. Now, there is some quirkiness to this, and the reason for the quirkiness is because when I trained this network, I knew I was going to want to run the conversion networks on it, right? As before, I'm applying 18 input events here for the 2 observations, and then I'm reading some number of output events. Right here I'm reading 7, but I'm going to have to count the outputs and then compare them. So I'm going to want to put some conversion networks on this. I'm going to want to put a conversion networks on each of these input neurons so that I can spike in a value instead of a spike train, and then they'll convert it to a spike train as before. And also, as before, we're going to append a voting network onto the output so that it'll do the comparison and then convert that into a single spike so that there's only one spike that's read as output rather than a whole bunch that have to be converted by the host. Okay? Now, there's a little bit of a problem with this. In the magic classification example, we always cleared the network between runs. So we could, when we ran the conversion networks at the beginning, the network was clean, nothing was happening, the original network. And then when we were converting the outputs, sure, the network kept running, but since we cleared it before the next observation, all was good. And we had that little K neuron that killed the outputs so that we didn't generate additional outputs. That approach won't work here. And the reason it won't is because since this is a control application, and especially we're not giving any velocity information, our neural network needs to have memory from one time step to the next. We don't clear it from one time step to the next. Okay, so that means we can't just add extra time steps to the network and expect it to work the way it did before, because that's going to corrupt the network state. So what we did to handle this issue was we did our training in a kind of three-step process. So for every observation, what we did was we ran the network for 33 time steps. Then we applied the input. Then we ran that, and we ran that for 24 time steps. That's when we counted the outputs, and then we ran it for an additional 28 time steps. And we did that over and over and over again. Okay, let's just look at a picture of that because it kind of helps to visualize it. All right, so here's how we trained. What we trained, we would run 33 time steps. That's running the network, okay? But it's not doing any input spikes. Then we do the input spikes in that middle 24 time steps, and that's also when we count the outputs. And then we run an additional 33 time steps at the end, and we do that all over and over again. Now, the reason why we do that is because that way we can add the conversion networks to it and not corrupt the way the network runs. So specifically, we're going to add conversion networks to convert values to spike trains. Those spike trains are actually going to start arriving here after the first however many, I guess it was an additional 28. So after 33 time steps, it's going to start emitting the spike trains over those 24 time steps. The network runs as it did before, and then we're going to isolate the outputs between these time steps, and then we're going to send those to that conversion network from figure 14 that does the counting and converting of spikes to a single spike. Okay, so in doing it in this way, we don't touch the original network, and we don't add anything additionally to it, so the running of this network is identically to when we ran it before the conversion. It's a little different from the classification, because the classification, we just killed the outputs and let it run extra time because we were clearing the network. Here we're not, so here we're taking extra care that we trained it to run in this way. Whoops. We trained it to run in this way so that we could add the conversions to the beginning, and then we could do the conversions at the ending, and the way the network is running is not corrupted at all. Okay, here's what that looks like. There's our picture here. Okay, so we have 8 conversion networks, one for each of the input neurons. That's going to take a value, convert it to a spike train. It says times 3 because the spikes are arriving now every third time step. So we actually multiply all the delays by 3. Okay, and then now we add a separate network here, which I have from figure 21. This network works so that it's only counting the spikes in those 24 time steps in the middle of the run. And those are the only time those spikes get through to figure 14. Otherwise, those spikes are squashed. It's basically an AND network. It sets up a neuron that spikes during those 24 time steps, and then it does ANDs with that neurons in these guys. And that's how it isolates those spikes. It's very simple. And then we have figure 14, again, doing the post-processing to turn these into single spikes. Okay. All right, now let's just see how it runs. So again, here's the original processor tool input. Okay, let's just go ahead and let's run it. Okay, so we're going to run it with the processor tool. So fro and processor. We'll do that, and then let's pipe that to head. Let's do 10. Okay, so there are this is running it for the first 5 time steps. Here are the output counts on the output neurons. So as you can see, that's going to go right, 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 right. First 5 actions are all go to the right. If we look here, well, here, let's grep. Spike. That, pipe that to head dash n 5, right? These should match, and they do. 5, 6, 5, 7, 5, 7, 5, 8. Okay, nice. Now the converted network, again, it's much bigger. I wrote a program to do it using the network tool, but I'm not going to go over that now because that's a lot of work. And so now what we're doing is let's take a look, and I converted the input. So let's go ahead and look at let's go ahead and look at the network. Okay, So network has a whole bunch of more neurons because we have all those input conversions. We have the output conversions to go through. Has more edges. Let's just take a look here. We have the inputs. Remember, before the inputs were 0 through 7 because we had 4 for x and 4 for theta. Here we have S, which is 91. Here I can prove that. Yep, that's S. And then each of those, each neuron here, 92, 97, 102, 107, is the one that you apply a value to, and then that gets converted, and that'll be a spike train going into 0, into 1, into 2, into 3, into 4, etc. Okay. The outputs here, remember the original outputs, I'm not even sure what the original outputs were. They were L and R. Well, we can look at it. Yeah, they were 8 and 9, right there. I guess we can do that. So the original outputs were 8 and 9. Now the outputs are 147, 148. And as before, there should be exactly one spike on one of these for, each time it's run. Okay, let's go ahead and run it. So here, let's run the processor tool. And now we're going to run it on this new converted one, and let's pipe that to head-n. Okay, so what we see is that these correspond to these, but instead of comparing, now you've got a 1 when this one was greater than, and then or 1 if this one is greater than or equal to. Okay. Also, here, let's just look at the input. Right, you'll notice the spike counts have been converted into values that get applied to the new neurons. And the run calls, instead of splitting the runs into 3 different run calls, there's just one big run call that runs for the sum of those times for 85. Now, I could change the outputs to look at neurons 8 and 9, but the problem is they might spike more than was reported by the other because the other just reported during those 24 time steps, whereas here it's going to report when they spike over all 85 time steps. So it's not very illustrative to look at that. If we really cared, we could look at the spike rasters and see how they match up. I'm going to say I don't care enough to do that right now at this point, although when I was debugging I did. Okay, let's just demonstrate that this works as we think it should, that these things match over all 15,000 time steps. And this is very similar to what we did with the magic example. Okay, so let's go ahead and let us grep for the actions. So let's grep for the actions in the original processor tool input. Okay, here, pipe that to head. All right, now let's isolate them. Oh, that's fine. Okay, so that isolates the last character, which is going to be a 1 or a 0. Now let's take that for all of them and put them into a file. Okay, so 15,001. There's an extra time step at the end. Okay, now what we're going to do is we're going to run the converted network, and then we will convert the outputs here so that they match the outputs here. Okay, so if we run this, okay, and then now let's grep for a 1 as the last character. Pipe that to head. Okay, so you see, right, when it's going right, it's neuron 148. When it's going left, it's neuron 147. Again, if I do a WC, this should be 15,001 because at each time step we get exactly 1 spike. Okay, now let's go ahead and convert the 147s to zeros and the 148s to 1. So said dot star nose s dot star 147 dot star 0. Pipe that to said dot star 148 dot star to 1. Let's pipe that to head just so we can make sure it worked. Beautiful. Now let's put that into a file. And if we diff that file in this one, so diff temp orig.txt and temp converted.txt, we should get that they're identical. Yay, they are. Okay, so that's showing that we're getting the exact same actions. Now that's not a proof that they're running identically. You'd have to do that and probably use the spike rasters to do that. But I don't have the energy to do that right now, and I'm not sure if it would really be illustrative to you or not. Hopefully, I've given you some hints on how you can go about probing things, seeing what's going on in your neural network, and debugging if you're creating networks like I happen to do. Okay, so that shows the conversion and the fact that they work identically. Let me just show our performance results again. Rendered this to an FPGA, each one of them. Ran it on a Basis 3 FPGA board. The host, again, is a Raspberry Pi microcontroller to keep things smoking fast. And what we get, again, in the original network, we have roughly 30 input packets and 30 output packets per time step. Whereas in the converted network, we have 7 and 5. Again, there are run calls. There's some things in there that it's not just the input spikes. But there are a couple more things that are in there. Again, the total number of bytes is much smaller, and the runtime, we get a factor of 4.31, which, again, is pretty big. Not as big as before, but then we were taking 48 and turning it into 1. Here we're taking 9 and turning it into 2. So it's a little bit less. But again, the results are significant, and it is a good way of training for one scenario, but then implementing it in another that's more efficient from a communication standpoint. All right, if you've made it this far in all of our videos, I want to say thank you for paying attention to it. I hope you've learned some stuff, and I hope that these conversion networks kind of excite you the way they excite me, because I think it's a real neat paradigm of separating out training and implementation and performance. Thank you.